Hello. We are Delta4, a biotech company leveraging the best of AI coupled with exceptional human expertise to discover new indications for drugs with known safety profiles. We're dedicated to accelerating new treatment options to improve the health of patients and get them into their hands faster and more safely than ever before. We're excited to show you how our unique and efficient workflow, centered around our proprietary software platform, Hyper-C, is used to uncover novel, mechanistically sound disease-drug relationships. We'll be sharing a real-world example illustrating the work we did with the drug Iguratimod. At the beginning of all new drug repositioning projects, we make sure to get a thorough overview of the background of the drug at hand, its targets, and mechanism of action. In our showcase, we're dealing with Iguratimod, which was initially developed as an anti-rheumatic drug and was approved for this indication in China and Japan in 2011 and 2012, respectively. While currently not being marketed in the US or Europe, Iguratimod has been garnering scientific attention in recent years, as shown by a growing number of publications. It has been shown to have broad anti-inflammatory and anti-fibrotic effects in several other diseases beyond the initially targeted indication. Our systematic overview of the current scientific literature enabled by OntoloViz, a tool we developed in-house, highlights the broad array of indications currently under investigation for this drug. These indications are in line with currently listed clinical trials, which, beyond the originally targeted indication, address several other disease areas, like inflammatory and autoimmune diseases such as lupus nephritis or Sjogren's syndrome. In order to understand how a drug may work in those different indications, a biological understanding of the mechanism of action and the role of the drug targets within the mechanisms is central. Based on a thorough review of the literature, we composed an illustrative schematic overview showing how the known Iguratimod drug targets are embedded in signaling cascades that ultimately trigger disease processes like inflammation, fibrosis, angiogenesis, or tumor cell proliferation, and osteoclast differentiation driving bone erosion, as well as how our drug of interest acts on these targets, in this case inhibiting them, to ameliorate these pathological processes. In addition to the role of the direct drug targets, we mapped the effects of Iguratimod on functionally related genes up and downstream of the targets reported in literature, in various disease contexts. All of this to help us build a mechanism of action molecular model for the drug and evaluate novel candidate indications during our indication screening process. Our proprietary Hyper-C platform lies at the core of building the molecular drug model. The platform integrates a vast array of data sources, including mined data from scientific literature, clinical trials, and patents, as well as drug and genetic databases, and data on biological pathways, disease processes, and protein interactions. The data is used to compose a molecular drug model with the drug targets at its core and extended by associated key genes and pathways. For Iguratimod, this process yielded a network consisting of 130 proteins, represented by network nodes, of which the drug targets are highlighted in red, linked by 649 network edges representing direct and indirect interactions between the proteins. In a biological context, these nodes can be grouped into 6 functional clusters representing biological processes involved in pathological pathways such as tissue remodeling and fibrosis or inflammation. In addition, analysis of network topological features help us understand the importance of each node within the overall network as well as to gauge their associations with the direct drug targets as measured by literature co-annotation. Not shown here for the sake of clarity, but we can use such node properties during the indication screening by weighting nodes in relation to their importance within a particular disease. During the indication screening, we take our molecular drug model and map it against our catalog of more than 3,400 disease models included in the Hyper-C platform, which were constructed in a similar fashion and with the same underlying data sources as previously explained for the drug model. For each disease model, we measure how properly our drug model fits the disease model. For example, the interference between the two networks using our graph alignment algorithms. To illustrate how this process works, let's consider a schematic example. Our drug model is represented here in red, and the network for our first disease, let's call it X, is shown in blue. The alignment is calculated based on an array of parameters, including the node overlap, a weighted similarity considering the gene disease association strength, statistical effect sizes, etc. The alignment of the two networks shows no overlap, so we don't have a match for disease X. The next disease, Y, shows a partial overlap. Disease Z is an even better match and thus would be considered the most promising candidate out of those three screened indications. In essence, this exercise was repeated automatically for all of the 3,400 plus indications included in our HyperC platform. In the figures shown here, each data point represents a disease or indication, which is plotted along two of the key parameters used to evaluate the network interference with our drug model. The color intensity of the data points indicates the overall ranking of the indication in the screening, based on an aggregate score of all the alignment parameters. In brief, if we look at where those indications that have made it into clinical trials rank in our screening, you'll notice that they are situated at least in the top 50%, most of them in the top 10%. So, if those indications hadn't been known already, chances are that we would have identified them with our approach. If we now look at all the indications that currently are still unexplored, for example those not tested yet in clinical trials or mentioned in scientific or patent literature, we can see that there's still a whole pool of potentially interesting indications left that rank in the top 1 to 10% of our screening. In fact, there's still a lot. More than 240. So to sharpen the focus, out of the top-ranking indications we shortlisted those with the highest association with the Iguratimod drug targets based on literature co-annotation for further in-depth evaluation. This is an excerpt of the list of 59 evaluated indications, including known indications, for reference. This is where we transition from AI, which we use to identify matches between drug and disease models, to human expertise for further evaluation of the indications based on in-depth mechanistic analysis by our molecular biologists. In addition, novelty and patentability, as well as business aspects, come into play at this stage to decide whether to pursue a given indication further. Ultimately, out of the vast space of more than 3,400 indications, our process uncovered 3 novel indications for our drug that satisfied all the parameters in terms of network interference, mechanistic plausibility, and novelty. These were a respiratory tract disease, a urogenital disease, and an eye disease. To illustrate what the network interference between drug and disease model looks like in practice, we're showing the match between our Iguratimod drug model to the left and one of our newly identified indications, a respiratory tract disease, to the right. The two models show a significant overlap in their network architecture and a high similarity score weighted by gene disease association. Furthermore, key pathological processes characterizing the disease are linked to our drug targets, giving additional support for the hypothesis that our drug can be effective in treating this particular disease. To sum up, we've illustrated our drug repurposing workflow, starting from a single drug and its drug targets, around which we built a molecular model that was subsequently used to screen against our disease model catalog. The initial screening based on the network interference allows us to create a ranked list of indications, which helps us select indications for further in-depth evaluation in an efficient manner, so that ultimately, we can boil down the huge list of 3,400 plus theoretically possible indications to just 3, which are novel and mechanistically plausible from a biological point of view.